And so started off with Squirrel. So go ahead, guys.
All right, well, thank you, ladies and gentlemen, for coming to our final capstone design presentation over the development of the secondary seal guide with partnership with Johnson & Johnson. A little bit about the team. My name is Cody Fintress. I was the project lead over this, helping out with some of the design and the programming with the robot.
My name is Elijah Garcia. I led the design and programming of the conveyor.
And my name is Colton Rigo. I did a lot with programming the robot and also doing a lot of the analysis.
So we're going to kind of give you an overview of what we're going to be talking about today. We're going to go over our project overview, some of kind of the constraints and standards that we had with working with Johnson & Johnson. We're going to look over the main design, overall design, and we're going to break that down into 4 sub-assemblies, and we'll dive deeper into each of the designs, both initial and final designs. We're going to look at some of the testing and assembly that went on over this last semester, as well as the finances, and end off on the conclusion. Hopefully, we did okay with our project. So with the project overview, just a little bit of background information with who Johnson & Johnson is. Johnson & Johnson are located here in San Angelo, Texas. They make medical sutures, so the ones where your doctors either sew you up. They produce over 30% of the world's market, and their process is fully automated. So the product will ride in these product magazines, and we'll go through each and every machine and won't touch the person's hand. The product here, as I show you right here, this is basically the product that they manufacture. They manufacture the sutures for this particular product. There are 8 different sutures that ride along in this one. They also have different sutures that either range from 6 or 4. For our particular project, we're going to be working mainly with the 8 of them. The product is going to be housed in what is called the product magazine. It has 4 individual compartments. The product will be stacked in layers of 30 in each of these 4 compartments. And this is what the product is transferred on throughout the entire process of Johnson & Johnson. Right here, again, we have some of those pictures of what the product magazine looks like, as well as what it looks like whenever it's inside the product magazine. What you're seeing right now is the current layout of the sterilization chamber. Our project mainly focuses on the sterilization area of Johnson & Johnson MedTech. And this is their crucial part to their process. They have to make sure that these sutures are fully sterilized to kill any of the bacteria or microorganisms that might be living on the sutures before they're finally processed. So first is the sterilization chamber. These product magazines will be what's called a pallet, and it will hold 24 of these product magazines. The pallet is able to shift left and right or up and down depending on what magazine is called next to be transferred onto what is called our fetcher station. The fetcher station is what our project is about. We are here to upgrade the fetcher station for their new auto sealer that they're going to have. So the main thing that our station does is it will grab the product magazine from the sterilization chamber, transfer it to our fetcher station, and then on to what's called their auto sealer. Now, like I told you beforehand, the product is not fully sealed yet to allow that EO gas to travel in there to kill any of the bacteria that they might have. What's important to realize is that this chamber right here that encompasses both the auto sealer and the fetcher station is its own chamber. It is under pressure of nitrogen. So what's really cool is that the sutures that sometimes are ran on the auto sealer, they do dissolve. So sometimes your doctor will tell you, hey, you don't have to come in because some of the sutures will just dissolve over time. That's because the suture will react with the oxygen in the air and will dissolve that suture for you. This is really critical to their process. This entire chamber is held underneath nitrogen so that it does not degrade that suture over time and the suture can be manufactured and sold. Once our station transfers that product magazine onto the auto sealer, it is then where it will be picked up out of the product magazine onto the auto sealer, and then it will be fully sealed from the outside world and will be ready for consumption. Once again, this is showing you the travel of where the product magazine goes. So it starts in the sterilization chamber, moves on to the fetcher station, on to the auto sealer. Now, I do want to point out a very critical part in our process. It's this 13-inch wall or window right here. This is very critical towards our project. We're having to design something that will reach inside that 13-inch window and will grab a hold of the product magazine and transfer it on. So please take notes on that. I'm going to show you a little bit about their process that they have right now. Currently, Johnson & Johnson uses what's called a magnetic coupling. What that is they use magnets that will ride on these 2 rails right here, and when it's sent an electrical impulse, it will either move forward or backwards depending on what is sent to it. you'll see that the product magazine is inside that window that I was talking about. Here's that 13-inch window we were talking about, as well as the depth, so it is 13 inches deep right here. They have what's called a single point load right now that Colton will get to later on. Their process will go and grab the magazine and pull it onto the auto sealer. Now there are a couple issues with this current design. It's unreliable, it has a short life cycle, it has extensive maintenance. So like I said beforehand, the whole entire chamber is filled with nitrogen. In order for them to go ahead and service all of this station or to do any maintenance work, they have to depressurize the chamber, repressurize it with oxygen, do all the maintenance, then depressurize it with oxygen and repressurize it with nitrogen. This is costly both in time and in money. So what's our project? Our project scope is to efficiently and effectively produce a working design that retrieves the product magazine in a timely manner and safely transfers the product to the auto sealer to be sealed for product consumption. Now I'm going to pass it over to Elijah to talk about our client constraints.
All right, and so our client's constraints are the requirements that they're needing for our project. And so first off, we have that it needs to be made of non-corrosive materials. And so again, this is to maintain that sterile environment to ensure no product is being damaged during this whole process. Next, we need a reliable magazine transfer to the next station. And so this means, again, with their magnetic coupling system they currently use, it fails relatively often. And so we want to ensure that we're going to be cutting down on that failure rate or completely eliminating it. Next, we have easy maintenance and serviceability. And so like Cody was saying, if they have to maintain, they have to shut down for hours, and it costs them a lot. And so being able to easily maintain and service ensures that production continues. We also want a minimum 10-year lifespan to ensure it's going to last them a good while. We also need our system to be compatible with Johnson & Johnson's programmable logic controller. Now that is a PLC, which is basically a sophisticated computer system that's used for automated processes. And so we're going to need our whole system to work in conjunction with their PLC. Next, we need to minimize the mechanism movement. And so basically, we don't want ours to be making multiple movements to retrieve that magazine. We want one fluid motion. That way, additional movements is just introducing more possibility for error or damaging product. Next, our frame must match existing designs for their auto sealer. And so we just want our frame to mesh seamlessly with their frame. And then finally, we want to limit product magazine damage. And so again, these magazines often get damaged on the front due to their current design, so we want to make sure that we can prevent that. And so here's a few client standards that we're following to ensure that we accomplish their objectives correctly. And so first off, we have a machine safety standard, which is basically just ensuring that we are identifying hazards and taking action to reduce and rid those hazards. Additionally, we have a clean room standard. And so again, that is to make sure that all of our components are complying and maintaining that sterility to keep product. And then next, we have an electrical safety standard. This is to ensure safety on all of our electrical components to make sure there's no hazards with any wiring and nobody can get hurt from that. And then finally, we have a robot safety standard here that is used to, that we're complying with to make sure that our robots are going to be safe to operate in this environment. And so here's a few more physical constraints. So because of the room that it's going into, and because it's going to be in that room with the auto sealer, we do have some physical constraints. And so our max footprint is going to be a 28-inch by 42-inch footprint. That's that Petro arm assembly location that Cody had showed you. Next, we have the 13-inch serialization wall. So again, Cody, whenever he was showing you that diagram, there was that 13-inch wall we're going to have to reach through. And so that's our next physical constraint. Next, we have the window that the Petro arm is actually going to have to reach through to grab the product is a 13-inch by 13-inch window. Finally, we need to ensure that our Petro arm is not going to contact the product while retrieving the magazine, because again, that could cause damage. And then finally, we want a continuous automated process to ensure that we are continuing Johnson & Johnson's automated process. Now I'm going to hand it back to Cody to go over some of our initial designs.
Thank you, Elijah. So we had some initial ideas when it came to how we're going to solve this. How are we going to make sure that we achieve all the objectives and make sure that we're inside all the standards. What you're seeing right here on the left-hand side is, again, part of that sterilization room right here, that 13-inch window space that I was talking about. This is the auto sealer, as well as this is the area that we have to work with. You see that 28 inches that Elijah was talking about earlier. This dotted line right here, this blue dotted line, represents the product magazine that will be transferring from the sterilizer onto our fetcher assembly, onto the auto sealer. And this was, again, just a basic sketch of the ideas, some of the ideas that we had moving forward. This right here is the full auto sealer assembly. So this is both the auto sealer as well as the addition of our new fetcher assembly right here. Again, the product will be moving from this area first onto our fetcher assembly, onto the auto sealer. Auto sealer will then be fully sterilized and fully blocked off from the outside world. What's really cool here, and one thing we designed for, is being able to stage a product magazine on our fetcher arm before the auto sealer is ready to call for another one to start processing all of that product. This will come into later when Elijah talks about some of the finances and stuff like that. This right here is our final fetcher arm assembly design. There are 4 main components. First, starting off with the frame. This is our structural integrity of our project. It allows for us to bolt it up to the auto sealer, as well as make sure that there's all the required holes for the motor or for the robot. Next, we have what is the conveyor. Elijah will go into more depth on his design for this, but the conveyor, again, is essentially moving the product, helping move the product magazine onto the auto sealer. Next, we have the fetcher arm. This is the tooling that's attached to the head of the robot right here, and will be the mechanism that goes ahead and will grab onto the front of the product magazine and start that process. And then finally, Colton will talk about the robot that we chose for our process. This is the mechanism that will be moving the fetcher arm and working simultaneously with the product magazine to complete our project. This is some more just the pictures of our design. It can be sometimes difficult to know what a 3D configuration will look like and the scale of what it looks like. And so you can see right here on the left-hand side some of the components I was talking about, the sub-assemblies. Here's the frame right here. We have the conveyor. Elijah will get into more of that. What you see here, here's the fetcher arm that I was talking about, as well as the robot right here. And now we're going to get into the sub-assembly breakdown. First off, we'll be talking about the frame. This is our initial frame design. It does fit within the specified areas that we need it to, which is one, it completes one of our goals. It matches up with the auto sealer design, which is one of the objectives that our client wanted us to make. It is designed to be made out of 1018 mild steel 1/8-inch square tubing. However, there are some issues with this design. First off, there is no conveyor height alignment or spacers that will go right here. Elijah will get into more of that, but essentially this is super important to make sure that our alignment with the fetcher arm conveyor is in the same alignment or the same plane as the auto sealer. If this does not happen, then the product magazine cannot transfer smoothly onto the auto sealer. Next, there is no way for us to bolt on our motor to run our conveyor. As you can see here, here's some square tubing that's actually in the way of that, and we do have to remove that. Lastly, or not lastly, we do have an area to bolt on our robot. However, this area or this location for the robot does not effectively maximize the total length that we have to work with our robot. So if we put it in this location, we would not be using that amount of length effectively. And lastly, we do not have any product magazine rail guides right here, so the product could easily run into the frame, could mess up our system and affect the transfer of the product magazine. So with our final frame design, it is still made out of the 1018 mild steel. It is now made out of actually 1/4-inch square tubing. The reasoning for this change is the accessibility of the material. We found out if we wanted the frame to be made out of that 1/8-inch square tubing, it was going to take us an additional 4 weeks to get that material in. We wanted to begin our production and welding of the frame, so we went ahead and went with the 1/4-inch square tubing. Now this does add to the weight. It's about 2 times as heavy as it should be, but that's okay because it does help mitigate some of the vibrations that Elijah's going to get to. To meet the standards of a clean room environment, it is powder coated. So you'll notice that this is steel, which is susceptible to rust. In order to complete that objective, we made sure that it is powder coated for us so that it's in a clean room environment. It does include those conveyor spacers that I was talking about previously to make sure that both the conveyors are in the same plane. It has our robot plate here. We have moved it to the far side, closest to the autosealer to again maximize that full reach of the robot that we have. It includes these Delrin side plates or those rail guides. Delrin is essentially a low friction polyurethane plastic. What that does is it helps the product magazine keep on its trajectory or that its path. If it for some reason does come in contact with the frame, it will just glance off and will continue to run along this course. And we do want to thank Johnson & Johnson for helping us machine this entire frame. Sorry, Fastline. I'm so sorry. Fastline for rolling up and Johnson & Johnson to help us with machining. And next I'll give it over to Elijah to talk about our conveyor design.
All right, so this is our initial conveyor designs. The point of our conveyor is to work in conjunction with the fetcher arm. And so as the fetcher arm is pulling the magazine, the conveyor will activate, continue the motion so that once the fetcher arm lets go, the conveyor will continue moving the product magazine onto the auto sealer. And so our design was using a two-belt design that's running through these two belt supports here. But some of the key components I want to point out are the location of the bearings on the outside of the pulleys that the belts will be running on. And then I also want to point out the small diameter and low profile of those pulleys. I'll get into a little more why that's important, but I just want to point them out for the time being. Additionally, I want to point out the rods here in the middle that are supporting the conveyor. And so they're supporting the supports that the belts will be riding on. And so I want to get into the issues that this design poses. And so here you can see our initial design was far too wide due to the bearings being located outside of the pulleys. And so this would cause issues in integrating it with our frame and our other components, that on our frame we will not have enough room to fit our robot and the motor for the conveyor. Next, the pulleys were, again, like I said, they were too small. And I'll get into the next slide. I can expand on that a little bit more, why that's such a big deal. Basically, the diameter of these pulleys were too small, so they actually sat lower than the bearings themselves. Additionally, this design did not have any belt guides, and so the belts would ride on these supports, and because there's no guides, it would have the ability to ride off of the supports, which would obviously cause a shutdown on the conveyor. The rods here, like I said, this design was based completely supported by rods, and so because of that, we felt it was too complicated of a design. There was too many components, and the precision that would be required to ensure that everything fit perfectly just created difficulties that were unnecessary on top of the requirement to add components to ensure that these are not going to slide back and forth on the rods. And then finally, this system did not have a belt tensioning system, and so any good conveyor needs a belt tensioning system to ensure that it's going to properly operate, and this one did not have that. And so to fix all these issues, we have our 7th iteration of the conveyor, or our final design. And so this design, you can see here, we moved the bearings in between the pulleys. This was to, again, bring that conveyor to a much smaller footprint to make sure that it fits well inside of our frame. But to ensure that that worked properly, if we had used the former pulleys, they were a small diameter, and the bearing actually sat higher than the pulleys, so the product magazine would contact the top of the bearing as it's being pulled into the conveyor. So to fix that, we did add larger diameter pulleys to ensure that we had the proper clearance over the bearings. And one thing I want to point out about these bearings and pulleys is they're the same bearings that Johnson & Johnson uses on some of their other conveyor systems. And so earlier in our constraints, we were pointing out that we want easy maintenance and serviceability, and so this is ensuring that we can keep that by using something they're familiar with, as well as the pulleys are the same brand that they've used on other conveyors. Next, I want to point out that this design reduces machining because, like I said earlier, with the other design, there was extra components and extra rods, versus this one has 3 main components with the 2 legs and the top plate, which is the entire frame of the conveyor. Next, we added plastic belt inserts into the belt guides. And so what these are doing is reducing friction. It's actually the same plastic that Cody had mentioned earlier, that Delrin plastic. It's a low friction plastic. And so the point of that is to reduce the friction on the underside of the belts, which will reduce wear and reduce strain on the motor. Additionally, these edges right here, without that plastic insert would be a sharp metal edge, that the belt would be riding on, and there would as well be a lot of wear and tear on those belts, which would reduce the service life of the conveyor. Next, we have a belt tensioner added here. That is a easy-to-use belt tensioner that I'll get a little bit more into in the next slide. But first, I want to thank Johnson & Johnson's machine shop for making all these pieces for us so that to help make our conveyor possible. And so here's a little bit more in-depth on our tensioner. And so what we did here, we added a cutout into the top plate to allow access to the tensioner here, which is functioning off of one bolt. And so the positives of this is it's easy to tension the belts. All you need is a ratchet or a wrench, and you can just tighten this one bolt, and it'll push this tensioner bracket forward, which on this side would be pushing those bearings forward and tensioning the belts. And so again, this goes to that key point that we wanted easy maintenance and serviceability. And finally, I want to go over the drive assembly for the conveyor. And I first want to say that for Johnson & Johnson in production, they will not be using the same motor. Like I was saying earlier, they have their own PLCs that they will use, and so they wanted to get their own motor and program it themselves for their automated process. And so our motor is purely for functionality purposes to demonstrate that everything works properly. And so to control that, we went with a Technic servo motor. And to control that, we used a Arduino microcontroller, which is a small logic controller that we have a lot of experience with that allows us to easily program the motor and integrate any extra components like sensors and buttons. And so now I'm going to pass it off to Colton to go over our initial fetcher arm design.
Yeah, thank you, Elijah. So we started off with our initial fetcher arm design. It started off with a 2-point contact design is what we named it. There are a lot of constraints with this fetcher arm design due to the constraints of this project. So we had to make sure it fits inside the window and also grab onto this magazine. The main issue with these magazines is a lot of them are bent due to other processes at Johnson & Johnson. And so the main thing we wanted to make sure is that it would retrieve it without any issues onto our conveyor system. So the material that we decided to choose is the 6061 aluminum. And so this is for the clean room, thinking of our clean room standards, and as well as making sure that it has a long life. Some of the main issues with our first iteration of our fetcher arm was we had some misalignment errors. So with these magazines being bent a lot, we were worried about it receiving onto our conveyor system and it not aligning correctly. So that was one of our big issues with this design. The next point was incorrect mounting configuration. So on the previous slide, we didn't have the correct mounting system to our robot, which we got later on. When we got the robot, we had to change a little bit in our design. The other third point we had was it was difficult to machine with the previous design. It was mostly, I think, 2 parts of aluminum, which was going to be really hard to machine. So we wanted to steer clear of issues with machining. And finally, we had an incorrect arm length. So with that, we made sure for our next design that we had enough length to grab the magazine through the window. And as you can see here, this is our 2-point load example. We also wanted to, we thought about maybe using a distributed load or just a flat bar. And so to figure out which one was the best option, we did a finite element analysis. And so we did their current process right now, which is the 1-point load, the 2-point load, which was our first design, and then the distributed load. And from here, this is only some of the information we got from ANSY's software. These are just some of the calculations that the software actually did. So this is total deformation for the 1-point was approximately 0.36 millimeters. The main issue with the 1-point load is there was no distribution of the load, so there was a lot of deformation. And basically what deformation is this magazine actually bends under the load. And then so for our 2-point load, we had a total deformation about 0.20 millimeters. And the main issue we had with it was the distribution errors when pulling it onto our actual conveyor system. So that was our biggest concern. And surprisingly, it actually had the lowest deformation. And finally, we have our distributed load, which had a total deformation of 0.26 millimeters. This one had a better consistent pulling system onto our conveyor system, which allowed us to be a little bit more confident in this design, and it was under our acceptable deformation in our scope. So finally, we wanted to make sure that our ANSYS was correct. So we then did a ANSYS test with also our physical test. And so what this will tell us is if our ANSYS tests were close to our real life test and if they were accurate. So then we used the ANSYS to add a stress probe, as you see in the red dot, and also added a stress or a strain gauge to the top of our actual magazine. We had another magazine that we added a strain gauge to, and with that, we were under a 10-pound load. We were able to find that the ANSYS result was 15.83 megapascals, and our physical strain gauge result was 16.26 megapascals. And from that, we could find that our percent error was 2.6%, which was super good. We were planning on trying to get it under 10, but 2.6 was validated our data. And so, just to iterate again, we did our finite element analysis. We ended up going with our distributed load. This is just some of the data that you can kind of see that 2-point was better overall, but distributed is the one we went with just because we wanted more consistent pulling of the magazine onto our conveyor system. So for our final fetcher arm design, we went with the distributed load, like I said earlier. With material, we kept the same material, the 6061 aluminum. We wanted to make sure that our robot connection was correct, so we double checked it, triple checked it. And we also designed for a longer arm design. And we would like to thank Johnson & Johnson for helping us machine this part. So initial automation ideas. So we had 3 ideas that we wanted to use for our automation system. The first one was our linear actuator, and basically what a linear actuator does is it's basically a screw on a gear system that would go retrieve the magazine. The main issue with this one is linear actuators are prone to shaving whenever they use the gears, so we wanted to make sure, for our standards, we want to make sure it's clean room and not damage the product. Finally, we did next pneumatic cylinder, and with the pneumatic cylinder, we had a huge physical constraint on our project, so we weren't able to use pneumatic cylinder just because we would have to position it in a real interesting way above it, and also it wouldn't be big enough to actually retrieve the magazine. And then, so finally, automated robot was our third option. We went through this to make sure that there were 6 axes that we could use, and also clean room standards. There was a lot of different options, as well as Johnson & Johnson's already familiar with Fanuc robots, so it was a better fit for our project. So finally, when we selected our automated solution, we've selected the Fanuc LR Mate 200 ID 7C. The 7C represents the 7-kilogram payload that the robot can actually pull. The 6 axes is the orientation. It has 6 axes of orientation that it actually can do. This one is considered a clean room robot, so it is suitable for sterile environments, as well as a greater than 100,000 hour operation life. We also wanted to keep in mind our electrical safety and our robot safety with our standards, as we said before. So assembly and testing. So this is a video of our first initial robot movements. We just wanted to make sure that the robot worked and just kind of start playing with our robot. As you can see here, there's kind of like a T on the end of our robot. We're kind of testing to see if we can keep that in a linear motion or keep the T in the same direction, just for testing. So then we had powering the robot. So this was another challenge that we weren't really expecting on how to power the actual robot. So we actually got a hold of ASU Facilities to help with wiring the actual robot. I had to wire these 3 connections into this circuit breaker. And then the other issue here at ASU is they didn't have a single phase 200 volt outlet. So we had to get a step up, step down transformer to be able to power the robot. And so Johnson & Johnson should have the adequate power to be able to power it and activate the plant. But here we had to end up getting a step down, step up transformer. So programming and teaching the robot. So this here is a teach pendant. And so what this does is it teaches the robot how to actually move. And so in this coding here, you can kind of see, this is called teach point programming is what it's called. And so what you do is you go through each point of the robot to program it where it's actually going to go. So this was just our kind of our initial testing with that. Then we had to actually program the robot with the tooling arm. So with the fetcher arm, we wanted to make sure that it had a long life cycle, even though it was pulling, close to 10 pounds. So what we had to do is the robot was used to be able to program its own tooling. And so it goes through a certain motion. It goes through like a 90-degree motion all the way to a negative 90-degree motion. And these are just some of the calculations that it came out with whenever you went through that process of programming it. And so we also had to input the weight of the actual fetcher arm tool. So here is the weight of the fetcher arm tooling. It's 1.32 kilograms or about 3 pounds. And then these are just some of the pictures of the robot actually on the frame and starting of the assembly. I'll pass it back to Elijah to talk about our conveyor system and frame.
All right, and so here on the left side in our first picture is our initial test, fit, and finish of some of our frame components and the robot plate. And then here is us test fitting the conveyor into that same assembly. And then here on the right side was our initial testing of wiring and programming the motor. Right here, it was programmed just to a button touch to ensure that we could get the motor operating properly. And then here on the left side, I want to kind of point out some of those key components I was mentioning earlier. And so here for our conveyor, on the left, we have the Arduino microcontroller that was operating the motor. And right next to that right here is a ultrasonic sensor. And so we use that so that whenever the fetcher arm retrieves the magazine as it passes by that sensor, it turns on the motor so that it's all one process once you start the robot. Here I also highlighted the grease points on the bearings. So I just wanted to highlight that we made them easy to access, again, for that point of easy serviceability and maintenance. And then here is a little bit clearer picture of the belt tensioner. And so again, as you're tightening that bolt, what it's doing is pushing these bearings forward and tensioning the belts. And so here I have a quick little video of some of our initial testing of the sensor, ensuring that the conveyor works as it's intended. So of course, hand goes in front of the sensor, it detects something in front of it, and it turns on the conveyor. And so here was our fetcher arm testing setup. So we're trying to simulate the setup that Johnson & Johnson has. And so here we have rails that the product magazine is sitting in, representing the pallet that the fetcher arm will be pulling them off of in production. Here is our test window that the fetcher arm needs to retrieve through. And so we ensure this is the proper size, 13 inches by 13 inches by 13 inches, to ensure that our fetcher arm can reach through the window without contacting the window or the product magazine and pull it out properly. And so here's a quick video of our first initial testing of the entire setup together. And so you're going to see the fetcher arm is going to go down, reach into the window, pull the product magazine, which is then going to initiate the conveyor. Now you're going to hear some vibrations because this was a failed test, and I'll explain a little bit more on that after. All right, and so obviously the robot did pull it and the conveyor did push it along. However, you notice all the vibrations is an issue. And so we, the cause of that issue is partly due to the conveyor belts. Once they're tensioned, they were making contact the bottom of the teeth on the conveyor belt were making contact with this sharp edge here on the plastic inserts. And so as it was contacting that, it was causing vibration. Additionally, once the belts were under tension, it was pulling this, it was pulling the drive assembly bearings out of alignment. And so that was also adding to vibration. And then we were also having issues with the gears on the shafts moving sideways as they weren't tight on one side. And so to fix all those issues, we rounded off the edge on the Delrin insert, and then we also made a more gradual increase. You can see right here, the height is shorter than right here, and it increases as we go along to make sure that the bottom side of that belt cannot catch. And then additionally, we added a spiral flexible shaft coupling, and so this allows for slight misalignment. So any issues where the drive shaft is not in line with the motor will not cause any vibrations. And then right here, you can see the shaft collars that we added to ensure that those pulleys are not going to walk away on us. And so here we have our final conveyor testing. And so this will run through the entire process again with some different angles so you can see the entire process. And that drop was just the magazine dropping onto the conveyor off of the rails. But as you can see, the entire magazine transfers through the conveyor, and we completely rid the vibration, so this was considered a successful test. And so now I'm going to pass it back to Colton to go over the finances for our project.
Yeah, thank you, Elijah. So our project had two big key points. Our total cost was $71,915 for the total project. The main parts was machining. Thank you to Johnson & Johnson and Fastline for machining our parts. We had a lot of parts considering our frame, our conveyor, and our fetcher arm, and we needed precision with those machine parts. So approximately 40% of our budget was going to machining, and then the other percentage was the robot. The robot cost about $30,000, which is about 50% of what we had in our budget. And the robot was a clean room robot, like we mentioned before, and also allowed us to be more precise with grabbing the magazine. So here is just some breakdowns of what Johnson & Johnson kind of makes right now. So one product magazine full of product is approximately $24,000. One pallet, like Cody talked about earlier, 24 magazines in a pallet is approximately $600,000. And then three pallets, which approximately gets run in about 10 hours, is $1.7 million. And so with the new Johnson & Johnson auto sealer system that they have, we will have to keep up with a 40% increase in production. And with that increase, you get $700,000 increase in revenue. And so now I'll pass it back to Cody for our conclusion.
Thank you, Colton. So again, I want to look over some of the risks that we were trying to mitigate over this entire process. I'm going to point out the major three. First off, we had the damages to the magazine. We made sure that we mitigated that risk by making sure that we have a distributed load so that we don't damage the front of that robot, of the product magazine, that the robot is able to precisely remove that product magazine. We have the Delrin plastic rail guides and the inserts to make sure that it does not scratch or damage that product magazine as well. Roller motor failure. Again, this is essentially just making sure that the motor runs correctly on it, that it does not, any of those bearings or gears don't come misaligned, so we made sure we mitigated that with the collars that we put on there. And finally, we had robot malfunctioning or corrosion. This was mitigated through Colton's center of mass or moment of inertia calculations to make sure that the service life of that robot was at the full extent that it could. And with all of our products that we had, we made sure that the robot was in the clean room area, and we either made our materials out of aluminum. If it was steel, it was all powder coated. I'm going to go back over some of the few client constraints that we had. Of course, like I just talked about, we had to make sure that all of our materials were non-corrosive. We had to make sure we had a minimum 10-year lifespan, and we had to limit the product magazine damage. Now going into our objective completions. Again, has to be non-corrosive. This was done by the clean room robot that we purchased. All the components are made out of aluminum or powder coated steel, and this is with the clean room standards that we set out at the beginning of this presentation. We had to make sure that we minimize the mechanism of movements. The magazine will transfer all in one motion. This was successfully completed whenever Elijah implemented that sensor that will then trigger as soon as the product magazine flags it, and then it will continue its process on to the auto sealer. We must be easy to maintain. This is completed with Elijah's design pre-tensioner. Again, it's very easy for them to access. It does not take much for them to tension those belts. We do have the bearing grease points. They're in an easy accessible area, so they don't have to lift off any of that top plate to get access to the grease points. And the bearings and pulleys are all brands used by J&J. So they have them in stock, or they have worked with the companies, so should be able to use any of those materials. We had to have a minimum of a 10-year lifespan. So if we assume that our robot runs in about a 10-minute cycle, which actually we actually think that it runs anywhere between 10 and 20 seconds. Johnson & Johnson runs about 61,000 yearly cycles. And if we do the calculations, that actually gives us, with the 100,000 hour operation, it will run for about 20 years with the appropriate maintenance. So we did complete our goal of having a minimum lifetime of 10 years. And lastly, our compatibility. We need to make sure that this will easily be implemented into Johnson & Johnson's auto sealer. And this is allowing for the PLC installation. Again, we're not using the motor that Johnson & Johnson is going to use and put on later, but all of the fit-ups, all the motor mounts are easily accessible and available for Johnson & Johnson. And again, that the project frame matches to the auto sealer frame. To finish out our presentation, we'd like to give some thank you to some very important people. Of course, our professor, Mike Brasher, who led over our capstone for the entire year. Dr. Garcia, he helped us out with our finite element analysis. We had David Greeley, who helped out with the 100-strain labs and all the materials we needed to construct all of our testing. We have Tom Campbell, who is the manager of the machine shop. Juan Melendez, who is our client and one of the engineers helping us out, along with Michael Martinez. We have Miss Olivia Castro, who helped us out with any purchasing that we had to make, either the new motor that we ordered or any couplings that Elijah had talked about. ASU Facilities is helping us out with hooking up all the electrical stuff for our robot. Kaylee Rigo, which is actually Colton Rigo's sister, she actually designed our logo for us. We have Mr. Sam Morgan, who was our sole machinist on this project, so we greatly appreciate his help on that. Of course, Fastline that did everything with the frame, purchasing that material, welding it all up, powder coating it, and finally, our ASU peers for any advice that they gave us throughout this entire semester. Thank you very much. We will now open up this time for questions for us. I'm sorry, not questions for y'all, but questions for us. If there are any.
You said it had to be reliable. Did you have a mean time between failures goal or mean number of cycles goal? What was the definition of being reliable?
So being reliable, made sure that, again, we hit that 10-year mark. We had to make sure that the robot isn't going to fail for any reason. So that's why Colton did all of the center of mass or the moment of inertia to make sure that all of the bearings.
But none of those are numbers. Did you have? I mean.
Did we have any projections of what we wanted to reach with yearly
yeah,
cycles?
Yeah.
We wanted to reach those 61,000 cycles. We got to keep up with the auto sealer.
Never mind.
For the plate that it's like the cartridge comes in, and then you have the two belts on either side. That middle plate, is there any like mitigation, or is it scratching, or the magazine scratching that plate when loaded?
No, so with the belts, they have enough clearance that it's gonna ride straight over that plate and doesn't
Okay.
come in contact.
We're developing it partially here at our labs and converting it to the Johnson & Johnson production. How are y'all keeping the clean room standards? Because I know our labs, as much as we try to maintain them, are as same standards.
Yeah, for sure. So first off, we tried to put it in one of the areas of the labs that did not have the most movement. That actually is the materials lab. So again, there is going to be some, we can't fully mitigate all of the dust or any, making sure that it's a completely clean room. But one of the ways we did that was, again, putting in the area that had the least amount of movement going on, making sure that there's no other projects being finished at the time, so any shavings or anything that happen. And then lastly, we'll be making sure that we clean that off before we transfer it over to Johnson & Johnson. Whenever they implement that back into their system, they'll do a full inspection and make sure that that's up to standards with all that they have, making sure that it's clean, making sure there's no oil or grease that's around any of the grease points for the bearings. We did that also, so anytime we did grease those bearings, we make sure to go back, make sure that there's no grease or anything that's falling out of those bearings. And then as well as the robot, it's fully encapsulated, so none of that's going to live for us. Yes, ma'am.
Will Johnson & Johnson be implementing your design?
Yes, ma'am. As soon as they get their own auto sealer up and running, this will be implemented up with their own auto sealer. So
Sadly, they had a accident, approximately December. They had a huge water main break, and it actually got their auto sealer a little wet, so I think they're gonna have to remachine their parts for their auto sealer, just so it'll be a little bit more longer of a timeline than what we were expecting for it to be implemented. So.
Excellent.
I'm curious about the robots. It seems to be like very powerful in many different ways. Is not like a little bit over designed for the test that they have? How do you choose the robot?
So we chose the robot based on, so Fanuc only has 2 clean room robots, and one of those got outsourced. We were gonna actually go with a 4-kilogram robot. It's a 4-kilogram payload, but they actually outsourced that robot. So the only robot they had was the 7-kilogram robot, and the one that we purchased was already being used for testing. They used it a lot for like showing off the robots and stuff. So we used that robot just for this project, just so we could cost save a little bit on that robot.
And to Colton's point, we actually talked with one of the Fanuc representatives. We went to Johnson & Johnson and measured how much force or how much load they would actually take for us to pull that product magazine off of the pallet. And the Fanuc representative was actually physically there with us. We did the full test in front of him, and so we went off of some of his expertise in terms of determining what robot would be the best for our application.
I guess the question is more about, at least in mine, is about the motion. You basically have almost just a linear motion. There's some kind of catchment motion in there, but you got a, how many degrees of freedom? 6 degrees of freedom robot, when what you really need is linear motion. So,
Correct.
so how did you decide to use the robot itself as opposed to some other mechanism for doing this?
Well, a big reason for that was our space constraint. So because we only had 28 inches of length, in order to get something that would like linearly reach in and grab it, well, we only had 28 inches of length, and we needed to reach in 13 inches to grab the product magazine, and then also pull the magazine at least halfway out to make sure it catches on the conveyor. And so because of that length restraint, anything like a pneumatic cylinder would have to be at least twice as long to pull that object. And so that was just, it would have had to hang way over the auto sealer. And so it was the physical constraint that was kind of one of the biggest reasons we went with it.
And did you look at different mechanisms at the beginning?
Yeah. Yes, sir, we did.
We also tried to
Linear
motorize
actuator.
linear actuators, but we found some that fit the size constraint, but they didn't have the power capability to pull the product.
And actually, I'll give a kudos to Juan Melendez back there. He was actually pushing us not to go with the robot because of the cost that it had. We actually met with him several times throughout the last semester. We pitched him the ideas of both the linear actuator and the pneumatic cylinder, but again, because they're not inside those room constraints that we have, and because of the shadings that could potentially get into the product, that's what essentially we went with the robot.
So you had issues with the vibration on the conveyor, and you said that your first test was a failure and your next one was a success. Is there a requirement on how much vibration can be in the conveyor portion of the movement?
So we didn't have any specific requirements, but we just wanted to get rid of it to make sure that there was, proper function, and that, because, I mean, if there is vibration, then, I mean, that could lead to more wear over time, and especially because a lot of the vibration was due to the wearing on the belts, and so we wanted to completely get rid of it, but there wasn't any specific requirement.
I guess, I mean, this is the second time you mentioned something where there's a requirement, you don't really have the target for it. the first one is about the mean, you know, what does it mean to be reliable, right? And so I would just point out that eventually you need to know what the real requirement is that they're shooting for. So like, I'm sure you have not totally eliminated the vibrations, right? Hopefully you eliminate them to the point where it's functional, but you know, when you're doing this, if you really need to know what's the actual requirement. So I'm sure there's going to be failures through your system. I don't know what the mean time between failures is. I don't know what the failure modes are, but if you want to talk about its reliability of the system, you need to be able to either measure or predict the reliability. If you walk into Johnson & Johnson, they got those numbers right up on the wall. They can tell you exactly what the mean time between failures of the systems are and how it's all operating. So I would guess that they'd have some goals for that.
I would think it'd be greater than, or less than the 4 to 5 hours that they actually have going on right
Yeah,
now.
but you need to quantify that and be shooting for the right target, right?
Go ahead, sorry.
Y'all had mentioned about the two-prong design being the more like numerically efficient design.
Correct.
But y'all went with the distributed load. Was there any way, if y'all had more time, to work on the two-point load to make it more reliable, or was it just easier to just go with the distributed load?
Well, so their product magazines, a lot of them get damaged, just not from the process that we're in. There's a lot of different robots that'll grab it and yank on it, and it'll deform like a whole bunch. So the main issue was with that, the teeth one of them would pull and the other one wouldn't make contact. So that was our main concern about that, and just the transfer of it. We wanted to make sure that even though it may be bent, there is some form of contact actually on the magazine. So that's why we kind of went with that. I'm sure that we could have. I don't know what else did we do.
Well, another factor of why we didn't go with that design is you can see these prongs are just one piece. You could make them, I guess, less less edges if you wanted to. But the amount of machining that it would take in comparison to the distributed load is actually a lot more. It could be more, I guess, more time consuming for Sam, who is actually over here machining all of our parts. So, and the other cool thing is if this fetcher arm, if anything on this breaks, we can easily detach it and put it in another piece, right? Instead of having just one solid design. If anything on this fails, we've got to shut down the entire machine, unbolt it, and then go get a new, basically remachine a new part for this. When instead we could have something in stock that would just be easy. Okay, maybe they have to shut down the machine. They can easily just unbolt it, put a new one on, rebolt it, and get back up and running.
You got your deflection calculations. So,
These
so
are all just some of them.
why is the 2-point load having lower deformation than the distributed load?
We talked to Dr. Garcia about that one. We weren't exactly sure why that calculation was like that, but it was last semester, so that bringing up cobwebs. But we knew that was not what we wanted, just because of the fact that these.
I mean, they're all acceptable.
Right,
The
right,
deformations are all acceptable. By the way, you had a nice target for what you needed, you met it, so.
Yeah.
Right.
Yeah, we're still a little bit confused on why. That could be something that could be on what we put into the system, right? What constraints did we put in? Did something happen with the meshing?
Or the boundary conditions. We did, so when you do a finite element analysis, you go through the convergence analysis to make sure you have the right mesh and ensure that we're in the right ballpark. So we make sure we try to cover all our bases when it came to that finite element analysis, but we're not sure if it's just because of the way we actually did.
How did you model the contact between did you assume that the boundary condition between the carrier and the arm was actually continued, it was in complete contact all the way along in the finite element analysis?
Correct, yes.
But that's clearly not true,
Right.
right? Because when it's bent, it's only going to contact it, when the carrier's bent, which they always are, right?
Right.
It's only going to contact it wherever it contacts it.
Yeah, they
Right,
have.
so we were given one of the 3D configurations of the product magazine, and so of course that's going to be in the most pristine condition. So
Yeah.
whenever you're actually modeling it, sure, you're not going to get one that's
Yeah.
actually bent, but
Which is, I
I
mean,
guess
mostly
I
trying to
don't
figure out
like
why,
it,
because it doesn't make sense to me.
One thing as well is we're measuring deformation or presenting deformation on this slide, but the thing that we really care about is that stress, right? You don't want to bring it past yielding
Right.
of the material. That's what's going to bend it. Was it under that yielding for the, I guess, aluminum material?
Yeah, so we didn't
Look
add
at
this
that
to
part.
the presentation.
Okay.
Elijah and I actually went ahead and tried to failure test the product magazine.
Yeah.
We used an engine hoist to hold the magazine. We put about 80 pounds on the magazine and it did not break on us. So, in terms of actual calculations and actual numbers
Mm-hmm.
ran by a software system, no, but we did do our own physical testing
Yeah,
to ensure
awesome.
that.
I'm trying to remember, did you do, was that linear simulation or non-linear simulation?
I think it was non-linear.
I think it was non-linear.
I think we did non-linear.
And it was more like a load, not a
Correct.
concept, right?
Yes.
And the load was following what type of load did you put? The load following keeping like the direction or accommodating to the direction?
Direction, yeah, we did direction.
Yeah, this was just a senior.
And we when we were doing that on AMCs, we made sure, so when we were actually doing the physical test of it pulling out of the pallet, we got 5 to 7 pounds of weight. And so I rounded up and just did 10 pounds, so worst case scenario. So these are a lot, they're a worst case scenario for what we did for our analysis.
Do we have time for one more question? Improvements, do you recommend any improvements, or given, one of the purpose of this project is that you get a full experience of project, and how confident do you feel about, doing a project industrial level? It's an industrial problem, of course. And can you also tell us about your learning curve over the year from courses that you have taken, and when getting a project, everything was taught in the class? Probably not. How did you train yourself to walk on that path? And the last one is, do you recommend any improvement on this design, given, say, if you're given another semester, for example, or lose some money, like, hey, what would you do?
That was a lot of questions.
Yeah. Because he said last one question, so I was like, I have to dump all of them.
Elijah, do you want to start?
Yeah, so as far as like further improvements, I would say there could be improvement in tensioning. Not necessarily the bracket itself, but more so on the other side, we had to add spacers to make sure that there was alignment for that motor and the drive assembly. So I think there's probably better ways that we could go about designing that to make sure that there is no no deflection or misalignment. As far as what I had to learn, I had to do a lot more SolidWorks than I had done before. I mean, I'd done SolidWorks in graphics class like my first year maybe, and I hadn't really messed with it a ton since then. So I had to kind of learn a lot more SolidWorks, but it was pretty beneficial because now I can go use that in industry that I have a lot more experience with SolidWorks. Yeah, and then just kind of like this semester, in machine and power, we're learning about gear design and all that. But of course, I had to get all that figured out last semester first. So it's kind of bad timing, but I'm able to kind of like relook at it now that I'm actually in the class and seeing what I'm going to do.
Yeah, I would say the biggest learning curve for me was probably learning how to program the robot. It took multiple hours. It took a lot of hours. It took a lot of different attempts. The main thing I was happy about, I actually wanted to be able to automate the whole robot, so by a push of a button, the robot would work. So that took a lot of phone calls to FNUC, begging Mr. Brasher to get us FNUC tutorials so we can go through that. So that was probably one of the bigger ones for me. The other thing was the ANSYS was the semester before. That was an interesting part. I've never really done any analysis like that before, so that was real interesting for me. And yeah, the project, I'd say the biggest thing that I would recommend Johnson & Johnson to look at is some of our conveyor parts, wherever we have the bearing and then the keyway. We would like to design that a little easier, so whenever they take off the belts, it'd be a lot quicker. But due to time constraint, we didn't get to design it as ease of maintenance as we wanted it to. So.
Yeah, so I was the project lead over this entire Capstone. I think one thing that I learned the most was how to manage a project, to make sure that I get on the timeline that is set forth before me, to make sure that I complete all the objectives of my client. And working with all of the different people in terms of Johnson & Johnson's machine shop, or as Fastline, making sure that I'm the communication between all of them, so making sure that my communication skills are at the level that it needs to be so that everyone is talking correctly, that will make sure that everything's lining up. As you can see, we did not have many issues, if any issues, in terms of alignment, which is really cool. So if you do have great communication, hopefully that works out for you. But in terms of what I've learned throughout this and some changes I would make, most of it would probably have to be with what Colton was talking about, with the keyways on the shafts, learning from a lot with Dr. Hawk's class this semester. We'd be sitting in class, and actually I turned over to Elijah and Colton and been like, that would have been nice to realize. And I've also learned that even though you work with some of the consultants, they tell you one thing, don't always trust them. We were told to use a clamp for one of our couplings, and it slipped on us, and we initially designed for a keyway, and we should have just gone with the keyway. But again, wouldn't have done that until we got to Dr. Hawk's class. Yeah, that's what I learned. Thank you all so much.
Thank you.
We will be having a demonstration at the Hunter Strain Lab. If you'd like to make your way over to the engineering building, we'll wait outside for you all. We'll walk inside and show you all the project. Thank you so much.